Screen. Okay, can you see that? Okay, great. Yeah, so hi everyone, I'm Emily. So we're going to have a little bit of change of pace and talk about direct imaging observations. So this is very much on the opposite end of the scale in terms of this is very low resolution spectroscopy. And I wanted to split this into two parts to kind of look at some simple ways of how we obtain flux values from images, and then also how to do a basic fit of an atmospheric model to a directly imaged companion. And so first of all, I just wanted to clarify a few acronyms and what I'm talking about. I'm obviously not going to go through the whole process of how we actually post-process direct imaging observations, but just some of the things that will help you understand the processes that I've outlined here. So when I talk about angular differential imaging, or ADI, I'm just talking about the observing sequence when we do direct imaging observations. So because when we're taking direct image, and it's quite literally that, taking a direct image of a companion next to a stellar host, the contrast ratios between the stellar host and the planet are obviously really, really extreme contrast ratios. And so in order to optimize the signal to noise ratio that we obtain from those observations, we use ADI to kind of derotate and stack the images on top of each other to add that signal together. So the things that are important to know here is the field rotates throughout the observation on the sky. So this just it correlates with the field here. And then the position between the pupil orientation of the telescope and the field or the sky object orientation is what's called the parallactic angle. And that's all you need to know for the purpose of this. So some of the ESO instruments that are capable of direct imaging observations are, of course, sphere and gravity on the interferometry side. And there's also, up until recently, NACO, which was recently decommissioned. So what I show here is just an example of some of the spectra that we may obtain from directly imaging companions. So these are either brown dwarfs or very massive planets. So these are all very cold companions that are very luminous and amenable to direct imaging observations. So I've shown here the wavelength range that's covered by sphere on the VLT. And so we have a combination of narrow band filters in the J, H, and K bands that are shown here, the full width half maximum of each of these dual bands. And then also this pink area here is what the integral field spectrograph of the sphere also covers this wavelength range. Then the different spectra, I'm just showing some examples here, are what we might expect the spectra of a brown dwarf or a massive giant gaseous planet to look like. So the sort of gray blue ones correspond to like T-type brown dwarfs that have strong absorption features from things like methane and water. And then we have these absorption features here are less strong when we talk about L-type brown dwarfs, for example, shown by the orange and pink one there. So now to get into things, so what you need to do is the two main packages that I will be using for this is the VIP, HCI, and species, which I'm going to talk a little bit about. I've already installed them onto my Google Colab environment, but make sure you run this when you go through this yourself. I haven't installed the PyDS9, but if you were interested in using the PDS9 environment in Google Colab, you can also do that, but it's not necessary. So I'm going to start here where we import the necessary packages that we need. So the first one I'm using to obtain the flux values for from the different images is the Vortex Imaging Processing Package, or VIP. And this is from Gomez-Gonzalez 2017, and the full documentation can be found at this link. This is just one example of many different processing, direct imaging processing packages. It's not necessarily the one I use or necessarily the best depending on the observations, but it's very user friendly. And so I think it's a good place to start. And it does have some really great tools within it. So I would definitely check it out in more detail. But here we're not going to go through the full processing of direct imaging data because that would be a whole workshop in itself. But rather we're just going to talk about the main elements that are required to pull out the photometry from these images. So you should be able to import the data from my GitHub, just using that there. And then and in this case, I'm just using a cube of some NACO data. So the setup for NACO and sphere data is very similar. They consist of cubes that are basically slices. In this case, we have 101 by 101 pixels on a 2D image. And these are just sliced across 61 different parallactic angles. So what I mentioned at the beginning with the angular differential imaging, we're just, each slice is just that different slice of the parallactic angle. And so we can load this in. And so we've got the cube itself, which is everything together, that 3-dimensional cube I just mentioned. So that's 61 slices. And then the angles are just this slice of those 61 angles I just mentioned, which are the parallactic angles. And then we have the point spread function, or the PSF of the star itself, which we use to do the fit. And this is just a 2D image of 39 by 39 pixels. So for this, we need to measure the full width half maximum by fitting a 2D Gaussian to the core of the PSF. And VIP has a nice little package to do this. So then we can see we're given the centroid in the X and Y axis and the full width half maximum. And just for the purpose of this, we'll just take the mean of the X and Y full width half maximum, which gives us a value of 4.6. So we then want to normalize the flux to 1 in a 1 times full width half maximum aperture, and then crop the PSF array. And this is what's going to be used to do the fitting to obtain the photometry that's required. So again, there's a very nice function within the VIP package that does this. And then we see that we obtain the flux in 1 times full width half maximum aperture there. And then we can plot this and see what it looks like. And it's a nice, very clean, pretty image. So there was some discussion previously about the pixel scale, and the pixel scale in imaging is extremely important because we need to understand how many arc seconds per pixel, especially when we're talking about astrometry, which I know is not the focus here, but these are all important because these variables are all entwined. So when we do this fit, we're fitting both for the position and the flux. And so it's important to understand the pixel scale of the object that we're looking at. So the pixel scale for NACO is already defined here, and then Sphere already has a well-defined pixel scale as well, which you can also load in using the VIP package. I'm just using this data set just because it's nice and clean and easy to look at. Another thing that we need to take into account is we need to recenter all of the frames in the ADI sequence. And this, like I said before, is to obtain this high signal to noise as possible. So if we just plot what this looks like before we've done any recentering, if we assume that the star is sat behind this donut in this dark region here, then we can see that this is off center. It's not quite as trivial as that, but just for the purposes of that, that's what we'll say. And this is the coronagraph where the stellar host that we aim the observations at sits behind. And this is to suppress as much of the primary starlight as possible because we're not interested in the star, we're interested in the companions we see around the star. But we need to make sure that all of these frames are centered together so that we actually obtain that high signal to noise. Okay, so then we can use a 2D Gaussian fit to shift the frames to the same central position. And VIP has a very nice way of doing this. So you can see here that we can look at the different pixels and the frame number and the shifts that it's undertaking in both the X and Y axis. And this is just using that Gaussian model that's implemented there. And then we can see what the shifts are like on here. If we just define the cube, and then let's check the first frame of the sequence after the shift was applied. And then we can see the difference here that we have this off center of the frame previously. And then this, once it's been shifted, we see that that it's nice and centered there. And we hope that all of them are centered in the sequence. So now to actually get on to how we do the fitting, because this is kind of the processing that's required before we get to this point. So one way that we mostly do this is to inject a fake negative point spread function using the normalized PSF that we calculated before. And so VIP has a nice package where we can inject companions. And you can see here that we can inject this companion at 0.83 arc seconds away from the central star, for example. And what we often use is principal component analysis to optimize the signal to noise ratio with the full frame ADI images. So again, VIP has a very nice package to do this that makes it straightforward. Just take a couple of seconds to run. And what we can see here is we can see the optimal number of principal components as a function of signal to noise. and how the flux in the forward path maximum aperture changes as you increase the number of principal components, which is what we expect. So if we then plot the frames, and we can see that we have this injected companion here that's been put into our images using the full ADI principal component analysis images. So if we look at we can look at the signal to noise ratio for a given pixel, and the mean of the background apertures as well, and the standard deviation. And this just gives us some information about this image that we're looking at here. So the way that the negative fake companion technique actually works is by the following steps. So first of all, we estimate the bias position and flux of the planet from the first reduced image, and then use the measured off-axis PSF as a template to remove the first estimate from the clean data cube, and then process the cube using principal components and component analysis, and then iterate on the position and the flux until a well-chosen function of merit is minimized. And you can choose what function of merit you want to do in this case. So that has this nice first guess module, which allows us to do this. And so if I start running this here, so as I said here, we obtain the first estimation by running just a grid minimization, and then we run now the mean minimization. And this is just the minimization of chi-squared by trying a grid of values for the flux. And this is why I said the position is also important as well, because you're simultaneously fitting for the position as well as the flux. And so knowing like the pixel scale is actually an important parameter in direct imaging observations. So in this case, simplex is set to true, which is the minimization that we're using in this case, and it's done using that preliminary guess of the initial grid minimization. So what it's done is it's stepped through a bunch of different fluxes, as you can see here on the x-axis, and then we have the reduced chi-squared, and we see that the most optimal number is around here at 300 and so. So this is the value of the contrast ratio between the stellar host and the companion that we are trying to observe. So everything essentially gets calibrated to that stellar host, and that's why it's important to understand what the point spread function looks like. And so it then runs, and what we get out is these three parameters here. So this is R, which is the radial distance between the stellar host and the companion. So that's the separation. And then we also have theta, which is the position angle of the companion on the image. And then we also have the flux value here, which is 350 or so. And that's the value in this case that we're interested in, because that's the value of the contrast between the stellar host and the companion that we're observing. So basically what you do is you go through all of the different wavelength ranges that you have in order to obtain a flux value for all of these different frames. So in this case, we're just going to do it for this one, just because it's quite a lengthy timing process. But if you were looking at sphere IFS data, for example, you have 39 different wavelength channels across the IFS, and then you would do it for each of those images. So you can use those values from the optimization to then subtract the planet, and we have this function here that allows us to do this.
Sorry? There's a question from Everett.
Yeah.
How to define the error on the flux value that you are measuring?
Okay, so yeah, I was going to get to that. So the thing because of sort of timing issues here, I am not doing a full sampling. So I'll mention it at the end of this little sequence here. But so normally I would couple this with MCMC, and then you would obtain the confidence intervals and the median values, and that's how you'd obtain the error. This is just a very, very simple way to do it, just to kind of understand the principle of how you do it. But I would usually couple this with MCMCs to actually pull out a more robust value. Yeah, which I was going to get to, but yeah. Yeah, so we just read in the values that we obtained before for R, theta, and flux. And then we build up these cubes using what we've obtained before. And then we can look at the PSF of the planet in the full frame principal component analysis final image I have here. So we have the two cropped frames, and what we see is this is the frame before the planet the injected companion has been taken away essentially. And then once we've injected that negative fake companion, what we see here is, well, we may have a small residual left over, but it's a pretty good fit, and we don't actually see any obvious artifacts from the injection of that companion. So that shows that it's a pretty good fit. So as I just said, to carry out a more robust way of doing this, both the flux and the position, the best way to do it is to couple it with MCMC and then sample the posterior distribution of parameters. And then this is how you'll generate error bars on each of these things as well. And then this is explained fully in this documentation. I just wanted to give like a first insight of the actual principle of how we do this, because it's quite a lengthy process and it can be quite complicated if you've never seen it before. And also another thing I haven't put in here is that for each wavelength channel, you need to correct for the stellar spectrum itself and any neutral density filters that were used during the observation. And again, given more time, then I would go through this, but I think it's kind of best to look at the analysis of the spectrum. So you would do this by convolving the contrast values that you've just calculated for each wavelength channel with the spectral energy distribution of the host star and the expected transmission from any of the filters. But for the next part of this exercise, I'm going to assume that this part has already been done, which is true for the spectrum that we'll work with. But this is really important to note that there is a step in the middle here that I've had to kind of skip through. So then the second part of this, I wanted to introduce this package called Species to just do some basic atmospheric model fitting. And so for this, I'm actually going to look at some sphere data that I published last year of a benchmark brown dwarf, HD 13724. And again, for this, if you want to read the full documentation, then the link is available here. But essentially, it is a great toolkit that contains lots of publicly available spectral libraries, atmospheric model spectra, evolutionary tracks. It's really a great place to start if you're interested in doing any fitting with directly imaged companions. So for this, again, we need to import the relevant Python packages. So for this, it's going to kick up a couple of errors with Pi multiness. I tried really hard to get this installed on the Google Colab environment, but it was not very happy with me. And so we're going to use a different nesting sampling algorithm just for the case of this. But what you can do is you can go into here and you can have a look. It's not very complicated to install it on your like personal laptop or whatever. Anyway, it was just a dependency thing, but don't worry about this error for now. You'll still be able to run it using a different algorithm. So then we need to import the spectrum for this brown dwarf, and this is just reconfiguring it as a FITS file just because I had it saved as an RDB file, but you had it saved as a text file or whatever, depending on the format, but this is just reconfiguring it. And then in this case, we want to specify the model that we're loading into our database, into our workflow that we're going to be using. So in this case, I've chosen the ATMO model, which is specifically designed for ultra cool brown dwarf objects that was published last year by Phillips et al. But just because I already know like approximately what the parameters of this object are, but you might not know it in the case that you're taking a first look at a spectrum of that object. And so you may want to play around with a whole bunch of different models. These aren't even all of the ones that are listed in Species, but I've just listed a bunch here that might be interesting to play around with. And what I would suggest you do after this tutorial is to go in your own time and like go and play around and look at these different models, because they probe different wavelength ranges, different effective temperature ranges, different surface gravities, and you'll see that you'll get slightly different fits for all of these things. So in this case, we're just going to use this ATMO model, but you could equally use any of these and see what kind of fits that you get. And so we need to also read in some information about the system itself. So we know the distance, we have the parallax, which in this case was taken from Gaia DR2. And then we've also have the fluxes that have been obtained using that negative fake planet injection that I spoke about before. And so we have each of the values here, which are the flux values themselves and the errors on those values. And these are across the J, H, and K bands. So we then want to initialize the species database, which we can just do using this here. And like I said before, we're going to add in the ATMO model into the workflow. So this is where you could then implement any one of those other models that I mentioned. And this isn't a complete exhaustive list of all the models available, but these are the ones that you might want to play around with and see what kind of fits you get on the objects. But in this case, we know the wavelength range that we're looking at for sphere is between, this is in microns, so between 0.8 and 2.8 microns. The spectral resolution in this case, I think, is specified by what spectral resolution is available for that specific model, which in this case is R of 1000. And then you can specify the temperature range. So you might not know the temperature range of the thing that you're looking at, or you might have some prior knowledge. It depends what kind of information you already have on the object. In this case, we know that it is within this temperature range because we've already done fits for this before and things, but you might have a wider temperature range depending on what you're looking at. And also different models specify different temperature ranges. So in this case, I think this is pretty much the full coverage of the temperature range of the ATMO model. As you can see in here, it's just adding in and unpacking those ATMO model spectra. And then we can see that we've got all the different grid points from 600 up to 1600 Kelvin, a surface gravity from 2.5 up to 5.5, which is perfect for what we want. So then we can also include the photometry and any spectroscopy that we already know from the list of photometry and spectra that were previously calculated values using the negative fit planet injection that I spoke about before. And this is the fit model using sphere in this case. And then we want to add in, I'm just going to start running this because it takes a minute to run and then go back and explain. So we want to add in the object that we're interested in. So here we have all of the information that we now require for the object. So we have the distance that was calculated before using the parallax from Gaia DR2. Then we have each of the fluxes in the narrowband filters from the 2 J bands, the 2 H bands, and the 2 K bands. And so we have both the flux values and the errors on those. Then we have the file name we're dealing with, the database tag, and then the wavelength range here. So this is in microns from 0.96 to 1.33 in this case, and the mean flux and the mean error on here. And the spectral resolution, so before we were talking about spectral resolutions of thousands or tens of thousands or hundreds of thousands even, spectral resolution sphere is 35, just to put it into context of what kind of low resolution things we're talking about here, because we're talking about these kind of very like broad molecular absorption features that we obtain through these direct imaging observations. So the first fit we want to do is a basic grid retrieval. And again, so we can, Species has this built-in fit model that just does the grid retrieval, which is really straightforward to use. And then we can put this between the effective temperatures that we had specified from the model before and the different radius that we might expect this companion to be. So this is a pretty broad range. And then we can include any previous photometry or spectroscopy that we spoke about before, so from the JHK bands previously. And we're fitting for these 5 parameters here, so the effective temperature, surface gravity, and the radius. These are the ones that we're primarily interested in for this particular fit. So this is now running. So after we've done the grid retrieval, we want to sample the posterior distributions. And in this case, I'm just using UltraNest, which is part of the species package, just because it's more straightforward to run in this case. But you could also use PyMultiNest. They're very similar. They're both nested sampling algorithms, and which are powerful in sampling multimodal distributions. So you can also do this using MC, for example, but I would recommend using either UltraNest or PyMultiNest. And like I said before, if you wanted to go back and try and install PyMultiNest yourself, it isn't too complicated. It was just a case of Google Colab issue, but you can go back and look at that documentation there, and it's explained very well. So this is kind of computationally expensive, like even just to do this basic run here that took a couple of minutes, but we can see that that's just finished running. And then we get the best fit parameters here. So we have the effective temperature, surface gravity, and radius. So then if we see what these look like in terms of, if we do a plot of the 1D and 2D projections of the posterior distributions, then we see the ones that we're actually interested in this case here are sort of these values. So we're talking about 1100 Kelvin, about 3.6 log G, and a radius of about 1 Jupiter radii, which is what we would sort of expect this kind of object to be, which is good. So then I'll quickly just run through these things because these are just pulling out the different samples using the posterior distribution that we've just calculated. So you can kind of go through this a bit more slowly in your own time, but this is just pulling out the relevant best fits from the median samples and the models that we require. And so yeah, we interpolate the grid with the best fit parameters, and then we have this model box. And then I will just quickly run through this just because a lot of this is just pulling out information that we've just calculated. And then you can also calculate the residuals of the best fit modules using this function here, which interpolates the grid at the specified parameters, as well as calculating synthetic photometry for the filters that have been provided. And then we can compute that synthetic photometry from the best fit model spectrum. And here you can just have a look and see what it is we're actually looking at in the synthetic photometry. And then finally, we can gather all of the results together in order to kind of obtain a nice spectrum at the end. So we pass all of these through the plot spectrum function. And then there's also a residual box, which is separately provided. And then you get a list of all of the filter names with the transmission profiles plotted as well. So you can kind of play around with this a bit and make the plot look however you would like it to look. And so what it looks like at the end is we have the top panels shows the transmission spectrum for each of the narrowband filters. So these are the J, H, and K narrowband filters. And that's just as a fraction of the transmission as a function of the wavelength. Then we have the purple points correspond to the sphere IFS data, in this case that we've fitted for. And then the black points correspond to the ERDIS sphere narrowband image points in the JHK bands. And so it shows the difference between the expected photometry at those different narrowbands and then the actual measured ones as well. And then we see the residuals down here as a delta flux as a function of wavelength in terms of sigma. So this isn't necessarily the best fit, like as you can see, but this is just to give an example of what you might expect this kind of thing to look like. And what I would say, I would encourage you to go back through and check all of those different models out and see if you can get a better fit or see how the fits look differently. If you tried to add in clouds, if you look at a clear atmosphere, for example. And so in this case, this is the temperature, surface gravity, and radius we look at. And you just to, as a comparison for what the published spectrum looks like, this was using different models, so we would expect the fit to look different. So it's the BT Settle and Wally 2012 models. But these are all kind of around around the same effective temperatures and things, but it can be somewhat difficult to pinpoint these things within such a precise error or whatever. But there you go. So at the end, you get this sort of nice spectrum. And like I said before, encourage you to go back through and add in the different models here and have a look around and see how those things change if you add in clouds, if you look at the different models as well. So I will leave it there. And if anyone has any questions, then you can ping me on Slack or whatever.
Thank you, Emily and Eliar. And we'll be heading to a coffee break, and then we'll reconvene at